we're going to talk a little bit about rational functions. So a rational function is of this form right here, r of x equals p of x over q. So all that basically means is that a rational function is a fraction. And generally, these functions will have an x value, or whatever your variable is, in the denominator. So I'd like you to pause the video and try these 4 problems. So recall that in order to find the domain of a rational function, you need to set the denominator equal to 0. And actually, I'm going to say that 12 plus x, my denominator, is not equal to 0. So that tells me that x is not equal to negative 12. So my domain is all x such that x is not equal to negative 12. 2 is a similar idea. Only difference with 2 is that I actually will end up with 2 things that I cannot have from my denominator. I have both positive and negative 3. So my domain for this one is all values of x, such that x is not equal to 3 and x is not equal to negative 3. Sorry, I ran out of room here. For number 3, if you try to set this denominator equal to 0, you actually get an imaginary number. We are not going to write that x is not equal to positive or negative 3i. That doesn't actually count with the domain. So we're just going to say that my domain is all real numbers. 4 is an interesting one. A lot of people notice that you can cancel out the x plus 1, which is nice. However, we still are going to be using that x plus 1 to determine what's not going to be in our domain. And we're going to talk a little bit more about problems like this later on. So both of these things in the denominator are going to give us values that we cannot have. So I cannot have negative 1 or positive 3. So just make sure on this one that you do include that negative 1. Don't lose that factor, because it still cannot be in the domain because you would still be dividing by 0 if you had that. I just want to talk about 2 really important functions that you're probably going to be seeing. I think that we've probably seen f of x equals 1 over x before, but I just want to make sure you understand what's going on with the graph of that one. So if you were to do an XY table, by the way, you don't need to do this every time, but if you were to do it, I usually like to do some negatives, I like to do some positives, I like to do 0. So you would end up getting a few things. You would get negative 1/2, you would get negative 1. When x is 0, we actually have our graph being undefined at that value. We get 1 and we would get 1/2 here. So you don't have to draw all of these points if you don't want to. I just want you to kind of know the shape. So I want you to know that we have a point at 1, 1, and we have a point at negative 1, negative 1. The other thing that's important is I want you to realize that when x equals 0, our graph is undefined. So it's going to kind of go like this. So this is the way my graph looks. Now, you might notice that when x is 0 and also when y is 0, the graph is going to not touch either the x-axis or the y-axis. However, as you go on and get closer and get higher and higher numbers, your graph is going to get closer and closer to those axes. And what we usually or often do when we're drawing these graphs is we draw an imaginary line or an invisible line. I draw a dotted line, and most of the time you're going to see it as dotted. And these lines are what we call asymptotes. So asymptotes are invisible lines that your graph gets closer and closer to, but never actually touches. So asymptotes are not they're technically not a part of the graph, but they're nice to draw just to kind of guide your graph drawing, just so you can remember we're not going to touch those, we're not going to cross those, we're just going to get closer and closer and closer to those lines. So whenever I grade these types of things, I will check to make sure you're not crossing over the asymptotes. So just be careful, make sure that you are getting closer and closer and closer to them. You can think that your graph kind of hugs against it. So then the second one, I don't think that we've seen this one before. F of x equals 1 over x squared. You're welcome to draw an XY table again. So our XY table, you would kind of find similar things. The only difference about this is that your Y values are going to be even smaller than the previous one, and they're all going to be positive. So, for example, when X is -2, Y is positive 1/4. These are the other values that you get. Again, when X is 0, my graph is undefined. So I'll draw a few of these. I'll draw the 1, 1, and the -1, 1. Those go like that. Everything else gets closer and closer and closer to my axes. So it's almost the same idea as what you had for 1 over x, except that the part on the left side is going to be flipped over because all my numbers are going to be positive. So this one ends up looking like that. And again, if you want to draw asymptotes, we have what we call a vertical asymptote at x equals 0, and we have a horizontal asymptote at y equals 0. You can draw them the same color, you can draw them in a different color. You can actually not draw them at all. Like I said before, they're not part of the graph. They're just more of a guide to help you know what the end behavior of the graph looks like. I'm going to give you a little bit of background information about asymptotes, and I'll actually give more details about finding them in another video. So we have 3 types of asymptotes: horizontal, vertical, and what we call oblique or slant asymptotes. So this is the general definition of a horizontal asymptote, and that is that y equals a value is a horizontal asymptote if the end behavior has y going towards L, or whatever your horizontal asymptote value. And it can be on either side. You can actually have 2 horizontal asymptotes. You might have one going to the positive direction, one going to the negative direction. Most of the time, however, we do only have one. You can have the graph crossing horizontal asymptotes. You will see a few examples where it does that. Most of the ones that we're going to have in the class are a little bit more straightforward. You won't usually cross them, but you might see 1 or 2 where you do cross it and that are a little bit more involved. Okay, so I'll give you an example. So if we have y equals 6 over x squared plus 1 minus 3, this one has a horizontal asymptote at -3, y equals -3. Basically what that means is that our x approaches positive infinity and negative infinity. Our y value is going to approach -3. And we actually write our horizontal asymptote as an equation. It is a horizontal line, so that means that it has a y equals in it. So make sure that you remember to include y equals. By the way, you don't need to be able to graph this one by hand. This type of thing I'd probably give to you, and maybe you would have to graph it on Desmos or something like that. So here's an example where there is a vertical asymptote. There's actually also a horizontal asymptote. If I have f of x equals x minus 2 over x minus 4, I have a vertical asymptote at x equals 4. Remember, once again, we are going to have our asymptote written as an equation. It is a vertical line, meaning that it has an equation with x equals a number. As a side note, there's also a horizontal asymptote at y equals 1. You might just want to recognize that. By the way, we will talk about how to find these in the next video. So for our third type of asymptote, this is the less common one. I'll show you how to do this. You're probably only going to have one of these on your quiz. The vertical and the horizontal are more important. You're going to be using those a lot more in calculus. But I just want to give you an example of what we call an oblique or a slant asymptote. By the way, the word oblique means slanted, in case you were wondering that. I'll probably call them both. I think your book refers to them as oblique asymptotes. It doesn't really matter to me which one you call it. So this one, I'll draw the asymptote first, and then I'll draw the graph. So this one has an asymptote at the line y equals x. Let's say slant asymptote at y equals x. So the graph of this one is kind of on, as x approaches infinity and as x approaches negative infinity, will kind of hug up against this. So I'll show you what it looks like. Kind of looks like that. And then this in that direction. So you'll notice that it doesn't touch. I'll draw this a little bit better. So it gets closer and closer in part of the way, but this one, it gets closer and closer to that line, but it never actually touches it, and it doesn't cross it in this case. So I am going to tell you that the graph of a function will never intersect a vertical asymptote. However, it can intersect a horizontal or an oblique asymptote. For now, with the oblique, you're not going to really have to worry about those types of things. We're going to probably just have one problem where you have to find it, and you also have to be able to recognize it. So that's all you need for the oblique asymptotes.